Okay, welcome students. Today is perhaps our last lecture of this semester. So far we have developed the two theories of superconductors. One is the London theory of superconductivity, and the other is the BCS theory of superconductivity. We have seen that both these theories are very successful in explaining the superconductivity and all its related phenomena. Now, the topic we will discuss today is the application of superconductivity. Not only the application, but this topic confirms the validity of the theory of superconductivity, because the phenomena is based on the theory of superconductivity. Now, this is the tunneling and the Josephson's effect. We will discuss the tunneling of these superelectrons, and we will discuss the Josephson's effect. Now, let me show you the relevant pages from Ali Umar to cover this topic. Okay, this is the page number 516 from the book by Ali Umar. Let me bring this page before you. Page 516. Okay, this is the page we are talking about, and you can see the topic in front of you in the article 10.8, tunneling and the Josephson's effect. Okay, let me go through the text over here, and I will keep explaining the underlying principles of this topic. Let us first discuss the tunneling. You know that when a thin junction involving a superconductor is prepared, tunneling may take place across the junction. Now, this is a quantum mechanical phenomena, well established and well stated earlier. Now, the tunneling current may be used to study the physical properties of the superconductor. Rather, we will calculate some parameters relating to the superconductors using this tunneling. So, if you look at figure 10.19, which shows a junction in which two pieces of metal, one in the superconducting and the other in the normal state, respectively, are joined by a thin insulating film. Okay, now this is the thin insulating film. On one side of this is a superconductor, and on the other side is the normal conductor. And the thickness of this film in between them is typically 50 angstrom. So you see it is a thin film, very thin. The film acts as a potential barrier as far as the flow of electrons across the junction is concerned. But because the film is thin, it does not completely inhibit the flow. According to quantum mechanics, electrons are still able to tunnel under a thin potential barrier. So, in figure 10.19, tunneling in a normal superconductor junction, this is figure A, tunneling dashed arrow is inhibited by the exclusion principle. Okay, let us go through the text and then you will focus on this tunneling. So if a small voltage V is applied across the junction, taking the field to be directed to the left, the energy band of the left side is raised by the amount electron volt, but the electrons are still unable to flow to the right because the states lying horizontally across are already occupied. Because of the superconducting energy gap delta naught shown here, so if the electrons want to tunnel through the insulator and come to the normal phase, this cannot happen because the right hand side is already filled by electrons. There is no space for electrons. So, but if the voltage is increased further so that the energy band of the superconductor is raised by delta naught over 2, and then the corresponding horizontal states on the right are now empty and the current proceeds to flow. So this will result in a current voltage characteristics shown in figure 10.19b. So we will now have a relationship between the current and the voltage applied as shown in figure 10.19b. Okay, delta naught over 2 is equal to the electron volts. The voltage at which the current begins to flow is such that delta naught over 2 is equal to electron volts, and from this the superconducting gap may be determined. So if we continue with developing the physical concepts, the above tunneling is referred to as normal or single electron tunneling because single electrons tunnel to the right. Another type of tunneling, one which involves is the Cooper pair, has received a great deal of attention recently and is responsible for the Josephson's effect. Now the underlying principle is that if the insulating film is very thin, of the order of 10 to the power 10 of the order of 10 angstroms, then the pair would not only tunnel radially across the junction, but also their quantum wave functions on both sides would be highly correlated. In fact, the effect of the film is merely to introduce a phase difference phi naught between the two parts. So look at the figure. Now this is figure 10.20, in which when the Cooper pair tunnels through the insulator introduces a phase difference equal to phi naught. So in the absence of any potential across the junction, the phase phi naught adjusts its value to that of the actual current, so that figure 10.34 is satisfied. Sorry, equation 10.34 is satisfied. So we have in fact, the effect of this film is merely to introduce a phase difference phi naught between the two parts of the wave function on opposite sides of the junction, as shown in figure 10.20. The current density across the junction is given in terms of this phase by the relation J is equal to J1 sin phi naught, where J1 is a measure of the probability of transition across the junctions. Now this equation is known as the equation of the DC Josephson's effect. In the absence of any potential difference across the junction, the phase phi naught adjusts its value to that of the actual current, so that equation 10.34 is satisfied. Let us now suppose that a static potential V naught is applied across the junction. We recall from quantum mechanics that the phase of the wave function is in quantum mechanics is given by delta phi equal to E into T over H cut, where E is the total energy of the system. Let us apply this to calculate the additional phase difference experienced by the Cooper pair as it tunnels across the junction. In this case, E is equal to 2eV naught, in which the factor 2 is introduced because the system here involves the pair of electrons, the Cooper pair. Therefore, delta phi will be equal to 2eV naught T over H cut, where T is the thickness of the thin insulating film, which now alters equation 10.34 to the new form that J is equal to J1 into sin phi naught plus delta phi, which is equal to J1 sin phi naught plus 2eV naught over H cut into T. Now this represents an alternating current, and this result is interesting because a static potential is seen to lead to the AC current, and the frequency of this current is given by omega equal to 2eV naught over H cut. It's steadily tuned by varying V naught. Numerically, nu is equal to 484 V naught gigahertz, where V naught is in millivolts. Now, since V naught is usually of the order of several millivolts, the Josephson's frequency falls in the microwave range. So equation 10.37 is in fact the equation of the AC Josephson's effect. So we have a DC Josephson's effect equation represented by the previous equation 10.34, and now we have the AC Josephson's effect described by the equation 10.37. V naught is usually of the order of several millivolts. The Josephson's frequency falls in the microwave range. The tunneling current 10.37 was observed very soon after it was first predicted by Josephson in 1962. One method of observation involves measuring the emission of microwave radiations from the junction. Agreement between theory and experiments is very good. The Josephson's effect has many applications. An important one is its recent use in the redetermination of the fundamental physical constants. We can see this from the fact that the frequency in equation 10.38 includes the ratio 2E over h cut, containing both the charge on the electron and the Planck's constant. It has been possible to determine this ratio to an accuracy of 6 parts per million. Okay, so Josephson's effect, both DC and AC, attracted the attention of the many physicists working in this area at that time, and is a very successful an effect which correlates the experimental observation with the theory developed by the Josephson, by the theory of superconductivity. Okay, now I would again request you to go through the chapter on superconductivity by Kittel, because after going through Aliumer, you will now be able to completely comprehend this chapter from Kittel, which has a more modern approach and will give you a more comprehensive picture of superconductors and all its related phenomena. So mind you that this chapter of superconductivity from Kittel is also included in your syllabus, and the topics we have covered from Aliumer are quite helpful in understanding that chapter, so I don't think you will have any difficulty in going through that chapter from Kittel. So that is also included in your syllabus. Okay, students, I think we have finished with the syllabus of your semester second course on solid state physics 2, and that will complete that completes the semester course on solid state physics, and now you are quite capable of for the examination. We may have a test before the final examination, and you now make yourself ready for this examination. Okay, thank you very much.
From the one.